So first of all, thanks a lot for the invitation. It's really a pleasure to give this talk at this venue, and specifically since the context of this semester seems to be foundation models, I'm very happy to share a little bit with you my experience of trying to build such foundation models for astronomy. And one of the goals for this presentation is to convey a little bit about what we're talking about, where we are talking about foundation models. So I'll try to leave plenty of time for questions at the end. We'll see. And please do not hesitate to ask any questions at the end if you want to understand a little bit better these concepts. But maybe the first plot that I want to show you is an illustration of the boom of deep learning and machine learning in astronomy and astrophysics. So what you see on this plot is the number of papers over the years. And at some point, I became too lazy. I didn't follow through for recent years, but it has exploded, the number of papers in AstroPH that are using the notion of deep learning, CNNs, and neural networks. So this is something that you're probably all very familiar with. There is a large number of papers these days that come out that use these methods. But one thing that's not so obvious when you just look at this plot is that the vast majority of these results have relied on the notion of supervised learning and on networks that are trained from scratch. And I want to first convey what this traditional way, and I'm using air quotes here, of doing machine learning has been so far. So what are we talking about when we talk about supervised learning? I'm going a little bit back to the basics. Is essentially, I'm going to use two notions here. The first one, that we're going to use neural networks, which are essentially just parametric functions that I'm just going to call f of theta here, that can take some inputs and are going to generate some outputs. So now this is your basic tool when you do deep learning or any sort of neural networks work. But in order to tune this tool to solve a particular task that you're interested in, when you use supervised learning, what you're going to try to do is to force your function that you have defined by a neural network to match some pre-existing true answers or labels that you may have for some particular example X, in order to reduce some cost function, typically a loss function that can look like this if you're trying to train a network to, for instance, estimate a parameter. So you need a large data set, D here, where you have examples of known like inputs and the right label associated to each of these inputs. So then doing machine learning on this kind of data set is just trying to optimize your neural networks to find the minimum of this loss function, such that when your network is trained, if you show it an example of data, it will give you an estimate of the answer just as close as what the true answer might have been in your known data set. So this is fine. This is a perfectly good way to do machine learning. But the important thing to see here is that this training strategy is very specific in two regards. It's allow you to solve a single task, to estimate a single answer, essentially, for each particular example that you get. And it is also trained very specifically to one particular data set. So why is that a problem in astronomy? Well, the issue, it comes in different flavors, this problem, but two examples that I want to show you here. The first one is that we usually are very limited in the number of training data. So these labels that we need in order to do supervised learning. So that can show up in several circumstances. The first one is, for instance, if I want to do machine learning in a regime that is fundamentally extremely limited in the availability of data, for instance, finding rare strong gravitational lenses that you can see here on the right, then I don't have enough of a large training set to train these big neural networks. The second case is that maybe I'm using simulations as the way to build a data set of examples and labels associated with it. But in that case, I will need to spend a significant amount of compute into building these simulations. And when I've trained a model on a particular set of simulation, it will typically only be applicable on that particular problem where it's been trained. And so that is this issue of limited reusability, is that even though in some cases I may have enough training data, it will always be a network trained once, and then it won't be able to translate to other problems. And so that has been essentially the way that we've been doing machine learning. It's been extremely successful. But meanwhile, while we were doing this in computer science, people have been doing something entirely different. And now we're trying to play catch up essentially with them to transpose their approach, their modern approach to deep learning to our domain. So what have they been doing? Essentially, over the last few years, we've seen the emergence of a new way of training neural networks that is based on this principle of foundation models. and this notion of supervised learning or self-supervised learning that I'll show you. So here, the premise is different. I'm going to start by assembling a large amount of data that can come from many different sources. It can be like the entire web text or all the images that you can find online. And it's not specifically tuned or crafted for a particular problem. What is important as well is that I do not have any labels associated with this data. So for instance, I can have a very large collection of images and no labels for what is contained on those images. But the idea is that I can use this pool of data to build what I will call a foundation model. We'll see how that works. And when that exists, I can then try to adapt that foundation model to the scientific task that I'm going to be interested in. And the key here is that this adaptation needs to be easy to do, very efficient in number of labels, examples, and very easy to implement. Okay, so this is pretty abstract. What would it look like in practice? So this notion of foundation models is exactly what allows ChatGPT, for instance, to work today. But this example on images is a little bit easier to conceptualize. So here, it's an example of training a large neural network to understand images without having access to labels of the images that you're going to train it on. So this particular model here is starting from an image, is only picking a few patches of that input image, then feeding those patches to a large neural network and asking the network to predict the missing patches of that image. So this is something that you can write down very easily just from having access to the image, no labels necessary. And what you can see here is that the training task that you use is no longer associated to trying to solve any particular scientific problem. But the good thing is that in order to solve this task, your network is going to need to generate a really complex understanding of the data. And what you see here on the right is examples of, for instance, when the network is trained, you can fit it with what you see here on the left, and you can ask it to generate the missing pieces. In order to do this, it needs to build a really strong representation of what images look like in the wild. And so then imagine that you've done that on a large amount of unlabeled data. The question becomes, how do I adapt this model to solve my scientific task? So this is illustrated here on this plot that you have on the left, where you have such a model that has been trained by essentially masking. And what you can do is that you can extract from this model an intermediate representation of the data. And this is the intermediate representation that it would use to solve the task that is used during pre-training. Well, it turns out that if I extract that intermediate representation and I use a very simple machine learning model on top of it, like a very 1 layer or 2 layers neural network, I can build a classification model on a small set of known labels for, let's say, classifying between cats and dogs. And it turns out that the classification accuracy that I can obtain by doing this adaptation after the fact is on par or better than training a classifier directly from images to trying to classify these things. And that has been the revolutionary insight that has transformed the field of machine learning in recent years, is that we are no longer restricted to data for which we have associated labels. So another way to see this trend is this plot that I show you here, which is in the context of an image classification challenge. And what you see here, first on the left of this plot, is the accuracy of different methods as a function of time, and methods that were restricted to training on supervised labeled data. So you can see that over time, the networks have started to become bigger and bigger, and the accuracy has increased, but it has plateaued and was never able to get beyond a given limit. And what you see on the right is the result of this foundation model approach, where these networks have been pre-trained with no labels, which means that you can pre-train them on a much larger amount of data, where acquiring labels for data is always costly. So you're no longer restricted by this. You can train literally on billions of images, and then you can very effectively adapt your model to the classification task. And by doing this, you can reach larger model, and those larger models are able to reach larger accuracy. So just to finish on this, I just want to highlight that there are different ways that you can do this adaptation. I've shown you this neural network layer, but there are other ways. For instance, in ChatGPT, you can adapt ChatGPT itself directly by prompting. So by adding some input information that will specify exactly what you want to obtain as the task. Linear probing is what I've shown you, is that you get a representation out of the model and you add a little piece on top of it, which is very simple. It can be as simple as linear projection, and you turn that into a predictor. But the only thing that you need to train at this point is this linear layer, which you can do with very few number of labels. And then the final way to adapt a model is what we would call fine-tuning, where you can further train the model specifically on your task. So these are ranked from like simple to implement to more difficult to implement. And at the end of the day, the best performance is usually obtained by full fine-tuning. This is more costly. You can still get state-of-the-art performance by just simple linear probing. And that's what we're going to see in our astronomical context. All right, so that's the premise of what is different from before to now. We're going to try to train these large models first, and then we're going to show that we can adapt them to different scientific tasks. What does that mean for us, and why are we interested? It means that we never have to retrain a neural network from scratch. So a lot of the time in neural network work and papers is always going into choosing the specific architecture, making sure you train it like specifically for your problem. This is very time consuming. And by time consuming, I mean, this can go to like several months of a PhD work going just into this phase, which now we can abstract away by just reusing an already trained network. The second thing is that if I can adapt these networks to solve complex tasks, even with very few examples, because again, it's just a matter of adapting the representation, I can now do like very complex analysis of Euclid or LSST in regimes where I only intrinsically have few number of examples. And finally, if I can reach state-of-the-art performance by simple analysis tools, and by simple analysis tools, I mean it becomes as easy as using scikit-learn, it means that anyone becomes a deep learning expert if you want, and you can deploy really complex analysis workflows at very low cost on your data. So this is very promising for us, but is it easy to do in astronomy? And what I'll show you now is that you know, it's not that easy to put in place, and we still have a lot of work ahead of us to standardize practices and to all adopt common tool bases. So the first point that I want to quickly touch on is that data is a significant difference between what we do in astro compared to what happens in computer science. So the first point is that in order to build those large foundation models, you need to have access to large corpora of uniform text, or data, I should say. This has happened in the last years in computer science, and people have built, for instance, this data set that you see here of 2+ billions of images and text pairs. So this is, you know, billion scale data set, and that's the size at which you can really build interesting foundation models. But in computer science, typically people are looking at images and text, which are very kind of standard and at this point easy to deal with type of data. But in astrophysics, we have to deal with additional complexity. So one of these additional challenges is that the metadata of your data matters. So here you have examples of 3 different images. They look at the same patch of the sky, but the images look different because they come from different instruments. So it's not going to be enough to just look at images. If I want to do scientific inference, I also need to keep track of where does this image come from and what are the observing conditions associated with that image. Beyond just images, we also have to deal with other sorts of data. Stephanie mentioned spectra. It can be more complex than that. We can have 3D data, like hyperspectral data, or time series, or a vast number of different measurements that are not standard in the same way that images and text are. And finally, the last point here is that accessing and formatting the data itself, this is a point that Stephanie also alluded on, requires significant amount of expertise, and it's typically not at the level that any machine learning scientist would be able to do something interesting from the data without some amount of curation. So to try to circumvent these issues, like a year ago at this point, we presented at NeurIPS this multimodal universe dataset, which was our attempt at trying to gather sufficiently large amounts of data in a consistent format such that we can do interesting large-scale machine learning on this. So I'm not going to go into all the detail of this, but I'll just tell you a little bit about what this project entails in order to go above these challenges that I've mentioned. we essentially relied on three important pillars. First, building a community, and that's something I want to emphasize here, especially to this audience, which is a great meeting point of several communities, and it really needs AI and astro experts to meet together and to work together. And we did this at a scale of about 30 people here in this project. Then we all sat down and agreed on conventions that depart from the traditional way that we've stored data in astrophysics, and that try to go closer to something that is closer to GPU training, essentially adopting conventions and good practices that come from the machine learning world. And finally, we also wanted to be broad in the data set that we were assembling, not focusing on one type of data, one type of scientific work, which is typically what has been done in the past, and instead being really broad in data collection. So I'm going to skip some of that. I'll just show you, flash you, two things. One, kind of a summary of the type of data that we assembled here. Hundreds of millions of images. It's not the billion scale, but it's still orders of magnitude larger than what people had collected before. We also have time series. We also have spectra, different sort of spectra. And it's all easily usable through Hugging Face datasets by simply a few lines of code. You can get started and you can get data in a standard format that you can feed to your GPUs. All right, so that's the first step. Now, the second step, imagine you have all of this data from essentially all instruments that ever looked at the sky. How are you going to work with it and put it in a consistent neural network? So here, I like to think about the spectrum of the way that you can build a neural network, from most specific, something that is excellent at dealing with one particular type of data. And this is something that we've been doing in the past. For instance, I've worked on building neural networks specifically dedicated to understanding the morphologies of galaxies. People in the audience here have developed similar things, but for spectra. But those were very specific architectures for very specific type of data. And if I want to think about the future, you could imagine that I can have one large neural network that can act on any type of data. And the most common denominator to any type of data would be the byte level representation of it. And people have shown that you can actually build a neural network that works effectively at the low level of the data directly by feeding the bytes of your JPEG images, and you can still do interesting machine learning on this. This is a little bit futuristic, future tech. We're not there yet in practice. I'll show you two generations of methods that we've developed in Polymathic. The first one that we call AstroClip, it was our first foundation model attempt. The way that it works is slightly different from what I've shown you in terms of like hiding pieces of images. This strategy for building a representation model is to build two encoders, one that acts on one modality and one that acts on another modality, and then having access to pairs of those modalities together and asking those two encoders to generate encoding that should align with each other. So, essentially be very well aligned when the encoding relates to, when the pairs relate to things that are associated with each other, and be very misaligned when I show it pairs of data that have nothing to do with each other. So that is essentially a key strategy that has allowed the first generation of image language models to emerge. It's been used by OpenAI to build some of their initial versions of image language models. And we've used it at Polymathic to build a first generation of model that can understand spectra, that can understand images, and that can map both of those type of data into a consistent space, a coherent space. Then that space has very interesting properties. So for instance, it has a property of similarity. So if I look at how different images or like galaxies are encoded in that space, here you have the nearest neighbor of the image in red. They tend to be very similar in shape, but they are also very similar in physical properties. And so that's something that you can use for doing downstream science. One of the other things that you can do is that embedding space is also very easily remapped into physical properties. So you can, in the same way that I mentioned at the beginning, you can have a mapping layer or mapping module that takes the embedding out of this large network here, and you can use it to build a predictor for some physical property you might be interested in. And so here with just a nearest neighbor prediction thing that you can do out of scikit-learn, you can build a predictor for stellar mass or redshift out of your model. And that essentially you can do in a matter of seconds from this pre-trained model. All right, I'm going to skip some of the results and some of the math, and I'm going to go to the new generation of models that we have released recently and presented at NeurIPS this year, which tries to go one step further and build one consistent model that can work on any data that you throw at it. So our starting point here, for this project was essentially what will make me happy. Where do I want to go? So the first consideration is that I want one model that I can use to operate on any input data. And that means that I never need to worry again about what architecture I'm going to use to analyze this data, or where should I go, etc. I can use one model and it will work on the data. And the second thing that we wanted to see in this project is some understanding of the data that should emerge through the self-supervised training that we can use for doing science. So unfortunately, I'm running out of time to go into all of the details. I'm just going to show you the diversity of data that we were able to throw at this model. We had images from different sort of instruments. We had spectra from different sorts of instruments again. And we also had different sort of measurements that were obtained from these different missions. We put everything inside a big pile, and then we have this strategy of what we call tokenization. Essentially, for any of these data modalities, we turn them into some standardized representation that is very similar to the way that language models represent text in terms of what we call tokens. And any type of data can be tokenized at that level. Once the data is tokenized, we can grab all of our data. We can build a really large model that learns to understand the relationship between any tokens, no matter what data or modality they come from, and understand the association between, for instance, image tokens and spectra tokens. I'm running out of time, so I won't have time to show you all the cool stuff that we can do with this. I'll just show you that with these sort of models, we can achieve what I kind of hinted at the beginning, is that this single model, we can now extract its embedding. It can be applied on any type of data, whether it's an image, a spectrum, or something else. And we can adapt that embedding to solve many different kinds of classes of problems of scientific interest. Here we show examples of predicting the morphology, the class of morphology of these galaxies. We can predict physical properties of these images here. We can even do segmentation of these images in terms of physical structures. And we can look for objects that are similar to known objects of interest. So for instance, finding more of these very rare strong gravitational lenses due to this notion of similarity in that latent space. And because I've noticed on some of the CosmicAI announcement that you guys are also interested in connection with text, I'll show you this very recent work that we put out last month, where we further learn a mapping between this embedding that our Aeon model has learned with language. And I'll encourage you to play with it. This link, Aeon search github.io, set up by Nolan, who was a student with us, that will allow you to play live with this query in natural language that is opening a new way of interacting with very large data sets. I'm going to stop here. Thank you very much for your attention. I'm very happy to answer any questions.
Great, thank you. So I think we can take questions online or in the room, and I already see Stephen online.
Thank you. This is really impressive work. I'm very impressed with what you've done. Could you comment on long-term maintainability of this? I noticed like Hugging Face datasets broke your API less than a year after you released Multimodal Universe. Aeon was trained on a version of MMU that isn't even public yet. How do we, incorporate new data sets and keep up with the rapidly changing landscape of the software?
Yeah, that's an excellent question. So I should say that our goal for the first version of the MMU was to get to a point where we could start to play this game of training large foundation models. It was not, it was outside of the scope of this initial effort to find a solution that would be sustainable over time and that can be, like a solution for an entire community. So moving forward, we're very invested in trying to find a better solution. By no means is our MMU in the way that it's currently set up the final form that we think this sort of things will take. And we're very much looking forward to work with other actors in the field to come up together with a way to standardize things and a way to make things community maintained and oriented. So to answer your question, this was the first iteration. We certainly don't think it's going to be the last one. And we're very much looking forward to work with the community on building a more sustainable model and with much better infrastructure moving forward.
Okay, we have a couple more online that I see. Dara?
Yeah, hi, thanks for a great talk. I'm curious about degeneracies in the models, like as you're training them with the different, multimode data sets and how you deal with that, and also about errors, how you might deal with errors in any of the, answers you come up with.
Excellent questions. Yeah. So two things. So degeneracies, you mean that data is maybe not 100% informative?
Or that the data, different combining data in different ways could lead to very similar answers. Degeneracies in the data input leading.
Oh, I see. Yeah. Okay, gotcha. Right. So this is a good question that goes to the core of how to use foundation models. We should say that this is fundamentally a generative model. I can use it to generate examples of data, and I have a few examples of that. These are examples of using this as a super resolution model, generating example of super result data. We are not advocating to use that mode of the model because, as you say, as you're hinted to, the most important thing for scientific usage of these models is to extremely well understand how errors are going to propagate and how to understand their predictions. So that's why the way that we advocate to use these models is in the following way, as an embedding model. And if you want to think about it, it's just changing the representation space of your data. You go from pixel to that abstract embedding space. This is just a remapping of the data. It can be bad, it can be good, that doesn't really matter. But once you have this embedding, you can then very specifically for a task, use that embedding and train an adaptation layer to solve your problem, the specific problem that you're interested in. And I can think of this stage, of this adaptation stage, as also a calibration stage, where I'm going to be very careful. I'm going to train that stage on very well understood data. And I'm going to also very carefully evaluate the uncertainties in that prediction at that stage. So this is very important. A foundation model, you never understand exactly how it's trained, on what data is trained, or like what subset of the data. And you always need to recalibrate its answer for the very specific problem that you're interested in. And that's what we can do with this notion of first encoding and then adapting very carefully for the specific problem.
Okay, thank you. So that makes sense to me. But so I guess what I'm hearing you say is that within the foundational model, though, there might be errors and degeneracies back there, and then you calibrate it at the end when you have a specific thing that you're talking about, or that
100%, yeah, because these are really big black boxes. They're extremely difficult to understand what they do. So I really would prefer this second phase of calibration to really understand what they do on a well-known problem.
Thank you so much.
Thank you.
Okay, so we're officially past time. I do see there's some conversation in the chat. So maybe, Francois, if you can take a look. I won't close, it does not close the Zoom link yet. But I suggest that if you have further follow-up questions, you can feel free to get in touch with the speakers. And then thank you everyone for coming. And thank you, Francois, again for an amazing talk.
Of course, thank you very much.